Good afternoon, everyone. I'm very happy to be here to talk about our recent research on affective computer interface. I think I stand here, I think I go back home because I worked at the RIKEN for 8.5 years. And 5 years I worked at the Nagoya Biomimetic Control Center. And then I moved to Waco for 3.5 years. 22 years ago, I returned to China, work at the Shanghai Jiaotong University. So I'm good experience support my this research. So this talk, I would like to report the 5 aspects in affective brain-computer interface. First one, we know emotion have a very long history in psychology. For example, there's many models. A very classic model, we can consider our emotion into 6 different and discrete emotion states. But all of this model is not computational model. We cannot directly use for affective computer interface. From neuroscience, we have 3 basic knowledge. First, we can look at the left fingers. So the emotion not respond so quickly, basically in the second and the minute. The second is the emotion is expressed not in single neural or circuit, instead in the system level. So for the right figure, we can see there's no physiological signal can express emotion. We can only inference emotion from different data. So this means in theory, there is no ground truth for emotion recognition or affective computing. So this is a very challenge for affective computing or affective brain-computer interface. We know this is a very famous book. The title is The Emotion Machine. In this book, Minsky argues persuasively that emotions, intuitions, and feelings are not different things, but different ways of thinking or our intelligence. So I think emotion is very important even for artificial intelligence. So what is affective brain-computer interface? We know BCI is a direct communication pathway between our brain and the external device. So affective brain-computer interface aims to enhance BCI with the ability to detect, process, and respond to our users' affective emotion or mood. So there are 2 main differences between motor BCI and affective BCI. The left figure is the framework of motor BCI. In this framework, our brain is controller, and the decoder and the actuator is a plant. But on the right figures, our brain is a plant. The decoder and the feedback is a controller. This is a very big difference between motor BCI and affective BCI. Another important characteristic of affective BCI is in affective BCI is a closed loop system, but in the motor BCI usually is an open system. Usually we use face, voice, texture, and other signals for emotion recognition, but there are several limitations for this signal. For example, for our face, our face cannot express or represent emotion in detail. So we needed a physiological signal. In the last more than 10 years, we focus on emotion recognition or emotion decoding in the dashed block. Now we want to combine emotion recognition and emotion regulation. So at the last, I would like to introduce our new project to depression assessment. The second part, I would like to introduce some deep learning algorithm developed in our lab for ABCI. The first one is multiple modality. As we know, we need to use multimodal to construct a emotion recognition model. So there's a trade-off between the model accuracy and the practical use. For example, in lab, we needed to use as many as possible signal. For example, from visual signal to EEG. But for practical usage, we want to reduce the cost of the devices. For example, we don't want to use the EEG signal because it is very difficult to use and the cost is expensive. Just 10 years ago, we proposed a framework combine EEG and eye tracking. This work was done by Weilong when he was a PhD student. So at that time, we used dry lectured EEG cap and eye tracking glasses to acquire the EEG signal and eye mode signal at the same time. So we observe that there's a very good performance if we combine those two signals. For example, in this paper, we can show for 3 different emotions. If we use EEG or use eye tracking data solely, the accuracy about 77%. If we combine those 2 signals, we can increase the accuracy about 10%. Why we can improve the performance? So we found that there's a complementary characteristic between EEG and the eye movement signal. From this figure, we can see for positive emotion, EEG signal have a very good performance. But for the negative emotion state, eye movement is better than EEG, especially it's difficult to discriminate negative and neutral. At that time, the eye movement have very lower error than EEG. So after this work, we also demonstrate on 3 different modalities, EEG, eye movement, and image. If you can acquire different signal at the same time, the number of modality is better than few. So another work, we want to simplify multimodal emotion recognition. Because, for example, EEG is very good signal, but for practical use, for example, if we want to develop a system used at home, and now the cost of EEG signal device is expensive. It needs a long time to acquire EEG signal. So at that time, a basic idea, we want to develop a model. At the training stage, we use the EEG, eye mode, and the other signal. But under the testing phase, we don't want the EEG signal. We would like to remove the EEG signal. This is the basic idea. So we propose a framework like this figure. So in the training stage, we have two parts. One part, we use multimodal feature fusion to extract the real multimodal features with a bimodal deep autoencoder. We can extend this framework to more than 2 number of modality. At the second stage, we adopt a conditional GAN network to generate the data. So at the last, as the testing phase, we don't need the EEG, we just input the eye mode data. This is the basic idea of this model. So we compared our proposed model with the traditional machine learning approach. For example, we can combine the eye movement signal with the EEG signal in traditional method. So the red one is our work. Even our method is not the best, but we can reduce the EEG signal in the testing stage. So for some real application case, I think this is a good method for reduce the cost or for considering the suitable for patient. So the third one, I would like to introduce a large EEG model. We know the large model was a big change for our machine learning society and AI. It's very successful in CV and NLP. My question is whether we can adopt the large model technology to EEG signal. This is our the basic question. So we have several challenges. For example, we have a shortage of EEG data and so on. So the basic idea is the same as NLP and CV. We use the self-supervised learning. Now, we also need to tokalization, similar to NLP, but some different. For example, in here, we can consider EEG data as the number of channel, total number of lanes, or some frequency. So we constructed the model with 2,500 hours EEG. In compared with NLP, it's quite small, but for EEG, it's largest model now in the world. So this figure shows the model size and the loss and the performance. From this figure, we can see the model size large, the loss can get quickly, as performance can be increased. We compare the performance between several downstream database with the performance of the state-of-the-art deep learning algorithm. We just show 2 examples. The first one is a 2-class classification problem, and the second one is the 6 classification problem. We have 3 models. One is base, second is large, and the third is huge. For the huge, we have 369 million parameters. So from those table, we can see our large EEG data is much better than the existing deep learning method. So this figure shows a relationship between the pre-training with or without downstream data set. From this figure, we can see our model can get a universal representation of EEG. I think we have, from this work, we have several contributions. The first one, we trained a large EEG. Now we continue to work. We have already trained a new model with 7,000 EEG data. The fourth one, I would like to introduce our data set we call the SEED. Now we have 8 subsets from 2015 to now. We continue to develop different data sets for emotion recognition and vigilance estimation. Welcome to use this data set to compare your algorithm with the SOTA algorithm. This is the figure shows the number of citations and application in recent years. From this figure, you can see the research now increased very quickly for affective computing and affective brain-computer interface. Last one, I would like to introduce how to apply the algorithm and technology to real-world application, considering the very challenging problem in China for depression diagnosis. So we would like to apply this technology to develop a system for objective assessment of depression. Our basic idea is we would like to transform depression symptom to emotional interaction task. So we need a lot of technology or algorithm. First one, we would develop an emotional interaction task. We would like to novel emotion stimuli paradigm, novel emotion stimuli material, and so on. So about 2 years ago, we developed a new emotion stimuli material. It's painting, oil painting. So this is the work my master student. For example, if you look the left figure, maybe you kind of feeling happy. Maybe stimuli is negative emotion state. So why we choose the oil painting? Very important point is that we want to use the eye tracking data because oil painting is a still image instead of a video. For video signal, it's difficult to analyze the signal. This is a real thing when patients looking at the oil painting. We can find a lot of useful information for depression diagnosis. This is our prototype. We call the emotion X-ray machine. This is we don't use the X-ray technology in here because X-ray we know know the function. So this is a performance of our emotion X-ray. Here we have the sensitivity and the specificity over 82% in comparison with the special clinical doctor. This is my talk. Thank you very much for your attention.
Thank you. Now for question time. Do you have any question?
Thank you very much for this beautiful presentation. So I have 2 questions. One is related to the emotions. As you mentioned by Minsky's book, we can use emotion for the communication. So basically, if you show me happy picture, I can have a negative response. I can have a sad response because this emotion is bringing some negative thoughts or memories. So how do you deal with those labels with the subject who sometimes have opposite responses to what you showed them? Because for your classifier, this is disaster because this EEG has opposite content to the label that you show coming from the picture.
This is a very good question for emotion recognitions. So we have recently just published this year's MAM, how to deal with the noise label data. Because we, from cognitive science and neuroscience, we know there's no ground truth for emotion. So at the first stage, we showed developed a very efficient emotion signalization paradigm and material. Now we let the subject to watching short video. So at first we collect 20 students to label the video. For example, if we look at the happy video, label the data from 1 to 5. If all the 22 students label the numbers bigger than 3, we consider this motion clip maybe stimulate the other subject in the real experiment. So I think there's a very challenge to how to label the data. I think one direction is we need to develop efficient material. Another, we need to use machine learning technology to remove the noise or to consider how to use a machine learning algorithm to enhance the model accuracy.
Okay. And if I can have a second question about eye tracking. So in the eye tracking, there's this famous experiment by Yarbus that the eye tracking pattern depends on the instruction. If I ask you, like, please look for the eyes, most people look at the eyes. Like, if I give the instruction, please look on the sky, the pattern will be different. So what kind of instruction you give to your subject to have standardized response, that they would have similar emotional eye tracks?
I think eye tracking is very good signal because in compare with the EEG, the signal is very easy to compare, to process. We have a result. If you look at the video, if you have full attention, the pattern, for example, we have 30 person here. We watch a movie. If you have full attention, the pattern is similar. If you watch the similar film, but maybe you have a double task. For example, maybe you talk with your friend and listen to music, the pattern is different. So I think the eye movement is a very good result. Even have a long history for medicine and other fields. I think we don't find the potential. There are a lot of space we should work on this field. Thank you for your problem.
Okay, any others?
Talk about large models for EEG data. So do you train the large model from the beginning, or you use pre-train the model to fine-tune to downstream tasks? Also, I'm wondering how much data set you need to train.
Very good question. At the beginning, because this work my PhD student, we have beginning, we just use the EEG. The next step we planning to not for initial EEG. We need to borrow the condition, for example, large language model. Before under the large language model, we train our model. I think there's a lot of space for this field. Unfortunately, we submitted our paper to NIFS this year, but I think the point is lower. So for recent work, we train a more large number model is about 500 million parameters. The performance is more better than this one, than the huge. So from our experiment, we can see the scaling law in each data. The more number of data, more number of parameters, the performance is better.
Thank you.
Okay, thank you.
Thank you.
Thank you.
But let me talk today about our recent approaches for the dementia biomarkers. And I'm a member of CBA team, so Cognitive Behavioral Assistive team. Our team leader, Dr. Otake Matsura, couldn't join today, so I will try to present our whole team as much as possible. This is one of our pictures. Our team is kind of divided into 3 sections: system, which is developing conversation support for cognitive health for elderly people. This is Dr. Otake's main goal. I am in the analysis team when we kind of develop methods for the measuring and kind of estimation, like, the well-being and biomarkers. And we have also evaluation team in our group, so you can see quite a big laboratory, which is based, like, of kind of judging how those systems are working. And in my today talk, as I'm very happy we had already BCI talks, I don't have to introduce many things, but I will try to kind of convince you about our transition from classical reactive BCI, when I will show you some example. Let's say affective BCI would be also reactive BCI because we measure brain interaction, but we slightly kind of go from control into so-called passive BCI when we try to use this technology to judge the well-being of the brain. And as we really focus on the well-being of our aging societies, in Japan, quite a huge problem. I believe also in China it's also growing because we are living longer. This is becoming a big problem. If you would be really interested in the topic, please visit my website, BCI Lab Info, that most of those information, all those updates are being put there. And just to advertise you, how the field is growing, we are organizing every year this BCI Neurotechnology Spring School. It's open school on the internet. We used to have 1,000, 2,000 students, and suddenly last year we had 82,000. So this is really nice, huge interest in this field. And this is not because there is huge revolution in BCI, mostly because these days machine learning is getting better. And those devices are getting cheaper, so more and more students can really enjoy it. So it's really showing there is really explosion in the brain-computer interface. So let me quickly review our former projects. As I told you, we are trying to use EEG, eye tracking, also FNIRS, and develop different devices like virtual reality, augmented reality. Those will be kind of preferable students' project. As we also try to use as much as possible machine learning, we kind of try to advertise that we are not so much interested in the artificial intelligence, which is for reproducing human being. That's not our job. We mostly kind of advertise intelligence augmentation. So basically, we want to build technologies using machine learning, using all these kind of recent developments to support, enhance, supplement our human beings. And also, as I used to show this slide very often, in the past, we mostly focus in the reactive BCA on the 3 modalities: vision, touch, and hearing, because they were very simple to implement. And I used to say in my lectures, it's impossible to use taste or smell or other modalities. But as I will show you at the end of this lecture, this year we finally challenged the smell, and it's really becoming very useful, and it's really fantastic intervention possibly for the elderly people. But that's at the end. So basically in the BCI, we mostly focus on the famous the oddball paradigm, when we try to classify the difference in the brain responses for the known stimuli, so-called P300 response, and those which we ignore. In the EEG, this is a difference of the 6 microvolts. So it's a teeny tiny signal. You see here grand mean average. Usual EEG signal will be crazy noisy. What we also could see in our former experiments with healthy subjects, as we modulated the difficulty of the task, so beginning of the brain response, it will be exactly the same for different, if you're attending, not attending, and so on. But once our cognition kick in, we can see the differences. So when subject is ignoring the stimuli, could be visual, auditory, tactile, there would be this kind of negative response. We call it flat. When it's usual, known picture for you, we'll have this kind of nice P300 response. But when we make the experiment a little more difficult, we could see that this P300 response was delayed and having lower amplitude. And this was our first actually hint that the difficulty of the task could be really seen in the brain response. And this is really very famous in the Alzheimer and dementia. Those subjects have very often those kind of delay responses, so this is the first model. So quick review on our old BCI, spelling devices. So we have it for the spelling in Japanese. Also very quickly we developed pinyin because we had one student who kind of realized actually Japanese, this kind of spelling A-I-U-E-O. In the pin also we have A-I-U-E-O actually. So even myself, I don't speak Chinese, but he just explained me, focus on this speaker, that speaker, so I kind of mentalized this task and I could type something in Chinese. We have quite many different tasks for the robot navigation, wheelchair, and so on. But that's the history. We also developed for Furukawa this musical BCI, and I am happy to announce that after 10 years of the break, we are returning to this project. That time, this brain musician could run at about 80% of the accuracy. So it was very kind of like slow, modern music. Quite often, a real musician had to help him to kind of cover up mistakes. This year, we are starting again because we have much better model. But just to show you quickly how this brain musician was playing. So the gentleman was memorizing and imagining 5 different musical notes. We mostly use visual cortex because he also used visualizations. And these concerts were done in public, people really enjoying. As you heard, it's a very slow music. We need like every second for classification. So it was very, very slow. But I really hope next year I show you a new demo, and this will be better. So let's talk about the passive BCI. When we don't care about the classification, about the control, we want to evaluate the well-being of the brain that is performing the BCI. And this is beautifully kind of fitting the idea of the AI for social good. It also fits the United Nations Sustainable Goal, like many companies like it. Goal number 3 would be good health and well-being for everybody. And we try to kind of like focus on this practical application. We are in this kind of goal-oriented group in the AIP. So when you look at all the numbers, it's really looking bad. Numbers of dementia will be growing. There will be like, for a moment, we estimate about 50 million people globally. This will be tripled by 2050. It's really bad. We know that also quite often the family members who take care of those elderly, they suffer also enormously. So there are many kind of like examples that actually the younger person who is taking care of the older one, it's dying early because the burden is so heavy. And financial cost of this kind of mental diseases, which is dementia, is really heavy. Luckily, already WHO, like World Health Organization, published around pamphlets suggesting that there are possible many interventions, non-pharmacological interventions. So we don't need any drugs. There is no drug actually for dementia, but we can change lifestyle, we can change our diet, we can change our social. So basically, we expect that many elderly people will be trying. Maybe I will do more sports, maybe I will do kind of more communication, but they would like to have some like measurement device. That's what we want to develop. Simple, like wearable AI or machine learning-based measurement device, which will help them to do it. So just quickly, if you want to think about Alzheimer's, this is like physically damaged brain. After the death, if you open the head, you can really see that brains of the people suffering from dementia are really kind of physically damaged. So for us engineers, we want to evaluate from outside if this brain is a healthy network, or maybe this brain is a damaged network. And we can really see, I will show you some results later, that from the complexity of the EEG signals, we can really evaluate that something is going wrong. When you think about dementia, this will be like late 40s, then the dementia starts. So majority of us, maybe many of us in this room, already with gray hair, we might think about this, like, if you want to measure yourself and have some like, alarm. Also from the medical papers, we know that 60 to 70% of dementias will be so-called Alzheimer's syndrome. So damage due to toxin, like, some like, amyloid beta and tau in our brain. So basically some garbage which we're accumulating. 10 to 20% will be so-called vascular dementia, which is related to our well-being of our vascular system, heart and so on. So if you can, like, develop technology that will cover both of them, we can cover up to 90% of the dementia cases. We want to look at the electrical signal of Alzheimer's, and in this case will be like optical signal for the vascular health. And all the other dementias hopefully will be also covered. Also, what is really nice in this topic of the research, this is really very active, like, topic. So basically last week there was published new report, and this is one of these medical papers when you have like hundreds of authors, but quite nicely, just to review this, they publish this report every 3 or 4 years. So in 2017, in the first of this paper, they kind of identify several like, points, so-called intervention, which we can do in the midlife and in the late life. In the 2020, they quickly updated and very quickly find there are more things we can do in the midlife and the late life, basically depression, drinking, and so on, which we can avoid. Everything is non-pharmacological. And the last week, they kind of shifted in the lesson report some of the interventions from the late life to the middle life. So it's really showing you that this is really active research, like, and this is Lancet, this is one of the top journals. What also is nice, at the beginning, they said that maybe 35% of our lifestyle could be modifiable. 3 years later, it's 40%, now it's 45%. So we really believe many people will keep trying, like, and for that, they need the device. So basically, again, from other medical papers, we have already many candidates. So luckily, like, from the neuroscience, we can set and evoke potentials. Some of you who do BCI P300, this is the famous P300, which is being delayed. We can also use at the spectrum and so on. On the optical side, we can use so-called FNIRS, when we basically use the optical, like, in this case, infrared light, which is illuminating, completely safe, completely healthy. Behind this wall, we have those devices. So basically, this will be FNIRS and the EEG. You put it in the single cap on the head, and you can measure both modalities. And this is really becoming like, lower cost this day. So as an engineer, if I can measure it, I can improve it, So this is basically one of this kind of take-home message. Also, Galilei said, measure what is measurable and make it measurable if it's not. So basically, we want to have a solid measurement. And these days, people just use this kind of boring paper and pencil test, which are super subjective, depending on the tester, who will be on the good mood and the bad mood. This person can have different, evaluations. We want to completely remove it and really develop this kind of technology that elderly persons, so basically now in laboratory, we have this kind of clinical level setup, but everything must be pushed, and maybe tensor decomposition could help with that we can really make those models very small and practical, maybe with the lower accuracy. So usual experiments will be like this kind of famous P300. You give instruction, please remember one figure, testing short-term memory. Then we show a series of the random pictures. One of them is the target. If a person has a short-term memory, there will be brain response. If it's not, there will be no response. So when we look at the beginning of the behavioral responses, we can really see that those people in danger zone, they have definitely already slower response. So even behavioral response would be slower. But those responses are really not trustful, because basically they have huge spread of those kind of errors and so on. So you can really see trend is okay. People with higher cognitive score would have faster responses, but we cannot really use it for the machine learning input. So that's why already at the beginning when I joined AIP, and this was work with Chibin, so basically at that time we tried to classify different P300s. So basically healthy person, cognitively strong, would have beautiful, again, 2 microvolts, what we call beautiful, nice response. People with the trouble would have the blue one, for kind of delayed and lower amplitude P300. Basically, in the BCI field, people mostly classify target versus non-target, so they have more difference. We are kind of doing more difficult tasks because we try to classify 2 different P300 responses. So that's why that time there was one of the NeurIPS workshops which showed this results. Classical methods for learning are just above the chance level. They really struggle with this kind of low signal-to-noise ratio. We had some deep learning model and also using some covariance like Riemannian geometry, but the best one that time, hitting 80%, was Chibin's tensor model, so that was kind of first collaboration for that. And then recently, last year already, we published new paper when we use kind of so-called network topology approach. So basically squeezing some information and recent publication from the neuroscience, when basically our experiments would be set up in the Simulink, plus some kind of capturing signals. This is much more easy. 10 years ago, doing an experiment was a major headache. These days there is so much open software, we can do it easily. So in this approach, which could be easily applied for the EEG and also for the eye tracking, we use a method called ordinal partition network, which is basically transferring our EEGs, which could be very noisy, having different amplitudes, into kind of permutation vectors. So basically we look at the values and we sort them according to the permutation. Then these permutation vectors are kind of building graph networks. So basically every new kind of node will be building new nodes, and we connect them together. So more complex signal would require more complex node. When we have simpler signal, more predictable, this graph would be simpler. What is also good for us, we do it everything separately for each channel. So again, if we would have one very noisy channel, this could be used as an outlier, and later we don't have to take it into classification. So basically we can convert everything into nice features, and just to show you kind of very rough graph in this case. So we will have on the left side very complex signal that require very complex graph, and already visually you can say much nodes, much edges. So basically we can compress again this information and just use this kind of feature for the input for the machine learning model. Very simple signal would have less nodes and will be less, in this case, edges also. So here is kind of connection maybe with the previous talk, because we are also using affective neuroscience. So basically for this experiment, we show our subjects short videos, and we teach them to evaluate them as usually psychologists will do. So we are testing short-term memory, troublesome for the elderly people, implicit procedural learning, spatio-temporal memory, and also emotion affect recognition. Those are short 5 seconds videos, so really kind of response will be faster and maybe more kind of obvious. So this would be short video. I will show you. So basically we have those videos. This is the database of the emotional videos.
We show them when this emotion is classified. Basically, this is like valence arousal, but our subject don't know the details. They have to kind of learn this thing. Then they put it on the touchpad. And then for the evaluation, we do it like, without this kind of prompt. So in this paper we published in the Frontiers in Human Neuroscience, we really can see that we have really significantly different responses. So those networks modeling EEG for the healthy versus MCI subject have significantly different number of edges and number of nodes. So it's quite nice. What is also for us fantastic, because this was based on one of the papers by the Professor Spohn's group, when they did a similar experiments with monkeys, giving them different level of the drug, which is basically reducing consciousness. And they could really see that EEG of the conscious monkey was more complex, while this kind of network were dropping as the strength of the drug was improved. So basically we can relate our results to our subjects who are healthy, that they will be more conscious, more aware, comparing to those subjects who are in the dementia, which basically their EEG patterns show lower awareness and lower, let's say, consciousness. We do some, in this case, unsupervised clustering, and you can really beautifully see those clusters are some kind of contamination, but basically this is really solid results. That's why we end up with quite simple classification models, starting from deep neural networks all the way to LDA and logistical regression. Everything will be around 90%, which is quite nice. And this would be kind of reproduced for different, in this case, our task. It's quite nice showing that this is really working, so we can use this kind of approach. In the second paper published in the Frontiers in Aging Neuroscience, so kind of higher impact, we also try to do it for the simpler task of kind of reminiscent images. So we show images from the childhood, Western style, Japanese style, and also modern. And we also can see that those results are quite similar. Maybe here processing pipeline is a little more complex, but again, we are kind of evaluating everything using topological data analysis and getting the classical features for the TDA, building kind of point of clouds, which again are significantly different. So basically, we can really see that EEG of the healthy versus dementia, those for the healthy will be more complex. When we try different clustering approaches, it's quite nice to show that we can kind of separate them. You can really see those TDA features are maybe less easy to separate comparing to the network neuroscience, but there will be again red versus blue. So blue is in this case healthy, and the red one will be MCI. Those clusters are kind of nicely growing separated. And what we really kind of also see in the classification results, having different subsets of the features, we can really find around 90%, 95% even, which is quite good using simple decision tree classifier. So again, this could be slowly maybe going for the product, many companies would sometimes talk with us. They say if you reach 95% and above, this is already kind of hopeful. But additionally, because when we use this kind of cognitive scores, we just use the binary, healthy versus MCI. But this is linear score. So we also try to attack regression. And in the case of regression, we can quite nice have an error of kind of ±2. And our mean average percentage error will be around 10%, which is quite nice. We are the score is from 0 to 30. So we are on the 3. It's kind of close to human being, because also those labels could be noisy. And also one of the reviewers gave us hard time. So we really review all possible classifiers. And now in this case, random forest was the best. But you can really see those features are quite solid. And the final one, it's olfactory. So as I said, quite often in the BCI, we are really afraid to start the smell sensation. But already in the recent paper in Frontiers Neuroscience was shown that elderly people who go from the olfactory enrichment and basically at night, they have small kind of olfactory stimulation. They go to sleep with different smell every night. And they could really see that those who are smelling water, control group, would have no change in the mental score, so this kind of dementia evaluation. But those who went for this kind of very simple intervention, it cannot be simple, you just stimulate the smell at night. And why we believe this is working, our olfactory bulb also very sensitive during COVID. Many of us who went through COVID, you can remember, first thing quite often was a smell problem, many flus and so on. But also in dementia, once you have a problem with smell, this could be very first sign. So our olfactory bulb is very sensitive. It's also the only sense we keep learning all our life. Vision, hearing, we kind of set up at the same time, we stop at the same time, but we always kind of have new smells coming. So our chemical sensors must be super sensitive. What is also nice, because this is such an active sense, it has direct projection to the hippocampus. And hippocampus in our brain is the main center for the memory formation. If your hippocampus is shrinking, you don't form memory, dementia starts. So if we can really stimulate our hippocampus, and this is very simple, like, it's like a muscle, like, you just present different smells, even overnight, and we stimulate hippocampus, there will be more hope for the memory formation. Also, I will use 2 minutes maybe. Also, in the very recent paper in the Nature Communication, our collaborator from Sweden developed new method when they put additional EEG electrodes, basically you move them from the scalp around the eyebrows. And as you can really remember, the olfactory bulb is just in the center. So this will be, let's say, EEG, they call it EBG, electrobulbography. Olfactory bulb is the kind of like, part of our brain which is pre-processing smell. So basically we can put those additional electrodes and get more information related to the smell sensation. So we published like last month, and also next month there will be one more presentation, several recent papers. So there will be by the Hubert Kasprzak, our student from Poland. He just became PhD student and he was our intern last month. So just quickly, just to show you, he even used very simple CSP. And what is nice, even in the CSP patterns, like linear filter, he could really see that the most contributing electrodes would be on the right temporal cortex. And this is nice, really confirming Dr. Sugiyama's paper from 2 years ago, who they published paper in the PNAS even, showing that the left cortex is the one that is mostly processing, in this case, olfactory stimulation. So basically, we nicely confirm it. When we go for the clustering, those clusters, in this case for the BCI, so this will be for the young subject, is really showing target versus non-target. But the results are not so fantastic still. This is very preliminary work, because half of our subjects are really struggling at the chance level. So it's really very personal. We have subjects going for the 100%, but some of them are really at the chance level. So we try to enhance those results, and that's why we combine the EEG and the EBG, those frontal electrodes, and you can really see those patterns are becoming more interesting. So EEG is really focusing on the right cortex very much, so it's good. And those two frontal electrodes are very nicely contributing to our signal. So this is multimodality we introduced here. And once we make this experiment again, basically we can go from the chance level using only EEG above chance level on the median, and when we combine those two modalities. So it's really worth, those two magic electrodes work. But still not being so happy that this result not so fantastic, we try to change the gears and try to classify if we can see from EEG if the subject will be good performance or the bad performance. So basically, in this case, we can classify how well they can recognize the smells. We ask them for the reports after each trial, how many smells they could recognize, and you can really see many subjects will have 6 smells, many subjects were running just on the chance level. So we split them into 2 groups, good performer versus the bad performance. Again, using only EBG, those electrodes, not so fantastic CSP, but basically different patterns. We are using only EEG, and then combination EEG and the EBG, both modalities, really show those patterns are nicely focusing on the front. So this is not BCI, this is cognitive load or well-being estimation. And again, quick review of the classifier. Clustering is beautiful here using UMAP. And then when we go to classifier using EEG in the EBG, almost 100%, only EEG dropping down, only using EBG dropping down. This will be for the random forest, very similar for the deep neural network. So it's really showing it's really worth to combine as many modalities as possible because you help your classifier. So just in conclusion, I really hope I show you some how machine learning can help and could be useful for our societies. We have to remember our societies are aging, so by building technological support could be quite useful, and we can help also ourselves age better. And we are very open for the collaboration. As you know, we need as many subjects as possible. So whoever would like to collaborate with us and bring us more experiments, also the machine learning side would be nice. Tomorrow, our student will be also presenting posters. So if you are interested, this is one of our recent posters using kind of musical approach. So this will be Simon Kojima tomorrow. He's Japanese, and he'll be presenting this tomorrow. Thank you so much.
Okay, thank you for excellent talk. Is time limit? We just take one quick question.
Thank you for your presentation. So in your dimensional study, how did you get the labels? From MoCA tests?
Yes, so we mostly use MoCA
tests. Are they discrete or continuous?
You continue. So MoCA score would be from 0 to 30. Our cases would be from around 20 to 30. So basically, I have one slide showing. Usually, those distributions are not fantastic, but let me show you. Oh, yeah, basically here. So this would be our MoCA scores in this case. So you can see we have, even 12. So basically different subjects. So there would be age distribution, and our Mocha score distribution. 25 is usually onset of MCI.
I see.
So this would be one class, this would be second class.
I see. So the other question is about, I think a more interesting question would be whether we can detect the onset of dementia.
Sure. So that's really our target, like,
do you think, is it possible to detect?
Yes, I think so. Like, if we can detect 25, this is the border, like,
Yeah.
So if you can make technology kind of reproduce Mocha test, but completely digitally, this will be the thing. And I believe people will go for different interventions. So there will be maybe traveling around here, oscillating. So you want to make regressions. So we don't want to use classification. There will be like a regression model. And like these days, you measure your blood pressure. People take medicine to kind of support their heart. They measure blood pressure. Oh, it's working like fantastically. So something similar I want to do, like, that easily at home. One day you go for a walk, you feel great. Wow, my cognitive scores improved. Second, lazy day, staying on the bed, dropping down, right? So there will be like daily tests in this case.
Right.
Yeah.
Okay. Thank you.
Thank you.
Okay, thank you again for an interesting talk.
Hello, everyone. This is Lin. It's a great honor to to introduce my recent research. I would call it the new generation. Yeah. So I will say actually this is a new generation of multimodal large language models. I just change its name. But the most important thing is like I'm doing it in an evolutionary approach. So basically, I want to briefly introduce myself. So basically, I'm not from like the engineering background, as I have told my colleagues so many times. My background was liberal education. For if you ask me what is my major, I will call you my major is in classics like Latin and ancient Greek, and I will show you some slides here. And at that time, I get my the therapist license. But then I didn't do any practice until 2021. Finally, I'm able to publish my first paper on clinical psychology, and then now I have to say I restart my career as a clinical psychologist. Okay, basically so then I went to, so from 2020, I joined RIKEN AIP as a research scientist here. So our team is called Medical Intelligence Team. So that's why, first of all, my research is on the medical research, like that. For example, normally we just publish papers on medical image analysis, TMI, and the things. So my research, I think I have to say, is quite, as I say, my research is very close to the real clinical things. I'm not really interested in the technical improvement or like the add-on or the things. I'm most important in the thing as like the textbook I have contributed last year is a practical guide for healthcare professionals. So basically in the clinical our clinical, there is a big gap. It's like that. For our engineering people, we're familiar with well-defined, simple, elegant, like the ground truth, like this is CAD, this is stock. But in the medical, it's totally different. As we say, in the medical, we're dealing with imperfect, uncertain things at all. So that's why what I'm doing is trying to link the medical things to the engineering things to bridge this gap. For example, this is our recent work, just accepted in the transaction on medical imaging. This is our top journal. So this is the first, what we are doing is a very important thing. We are the first one to show that. So because normally when we are doing see the doctor, we assume doctor know everything, but actually doctor almost know nothing. So in the report, as you can see, most of the reports, they will say, okay, the right line is likely atelectasis. And for example, there is like the small right things or stable Maya things, or like we will say the patchy left base opacity may be due to the thing. If you really read the report, you will know that actually in our clinical practice, this is most of the time we are writing the things here. So we are the first one to show that. To extract this the uncertainty and severity as extracted into the benchmark. So, but this research is not about technical at all. Yeah, so we don't have the luxury to use any techniques here, but we are just set up the first benchmark to at first tell everyone, okay, uncertainty and the severity is important, and now we have the benchmark. You can just play on this data set. Then the second one is like that. We also have a paper on the medical data set for the multimodal large language. So just like last paper, that paper was joint work with NIH and Medical Cancer Center in Japan. And this is also a work with NIH and National Cancer Center. So basically, we try to get a data set. So like we know that in the multimodal large language model and the medical data set, the most important thing is like you lack the data set. And as also like in the Nature paper just by the Oxford, they show that if you just synthesize the data set and then it will just point at the large language model and then you will get nothing. That's why in large language model, the most important thing is to get the high quality data set. And then with working with NIH and National Cancer Center, we just follow the doctors, that we follow the clinical practice. As you can see, like when the doctor see the image, then how will he think? For example, where is abnormality or is there an edema? And then what is abnormality and what's the level and the things. And then we just use LLM to help us to construct a very high quality, large scale VQA data set to help to train the multimodal large language model. So basically, the first work is published in the KDD, and then this one is now here. So basically, like the Gemini and the medical PEP and all the medical, like the data set, the large language model you can name, actually has used our data set already. So basically, this is what we're doing. It's like in the clinical research, medical research, I'm not interested in the engineering details, but I'm more really interested in how it can be translated to the doctors, to the clinical output. And then I'm also a PI as a moonshot project. So the goal is very large. So it says it can be help the people from limitation, like from body, brain, and by 2050. So the good thing is the goal is big and the money is big. Yeah, that's all. Yeah. The third one is like I'm also a PI for the RIKEN Most project. I think Qibing also have one. Yeah, I think many of us have this one. Yeah, I'm now working with the Zhejiang University Hospital. So basically, they are expert in schizophrenia. So but remember, I'm also a therapist, but didn't do anything. So thanks to them, I can now restart my career on the therapist. So basically, we're doing the subtyping and early diagnosis of schizophrenia with AI, and then we're doing it in the RDoC framework. So RDoC framework has been talked for so many years, but now actually still the big gap is like the gap is quite big. So we hope that with our AI techniques, we can just really bridge the RDoC to the real clinical output. So I will just introduce some our research. So as the psychologist, normally we think that the people just recognize the world in these steps. First of all, we are actually facing a real world signals which are continuous and high dimension. Then our human brain will decompose this physical signal into discrete symbols, stable units. And then in the machine learning, we call it the tokenization. And then from the tokenization, we just get from the spectral become the colors, pixels become the object. And then we just abstract them into the language, which is words and sentence. And finally, they can be summarized as knowledge. Then during this time, attention is all you need, that we have the attention mechanism to do the control all the things. So this pipeline explains a very important thing, why computer vision is lagged behind. For example, in 2012, the current deep learning is why we call deep is because we have the AlexNet, which works on the computer vision. So computer vision, most of the computer, in the deep learning, the progress in the deep learning were made in the computer vision, as you can see, the different networks make it deeper, the larger. But then this years, 2 years ago, we find that LLM has achieved great success. Why computer vision is lagged behind? The reason is that, in the computer vision, if we just follow that pipeline, we can see that for the computer vision, actually, it is more likely to directly deal with the real world, with the 3 megabit image, and then you have to extract the feature, but because it's too big, you have to extract features and then use a specific architecture to do the output. But in the large language model, we can see that actually here is our human brain. Our human brain, thanks to the knowledge and the ability acquired during evolution, we can just summarize the image into less than 20 bits words, and then put this sentence into, use this sentence to to throw it to large language model. So actually, the success of large language model is like before that large language model is actually have our human brain, but we normally didn't notice that. And also like that, so that's why, as we can summarize that, the representation like language is a pivotal or is a post-star that in the recent research, for example, like large language model, you change the image into a language, and in generative model, you change the language into the image. Yeah, so basically that's what I'm doing here, like follows the things. So my research are mainly 3 parts. First of all, physics-centric learning that can directly deal with the world, and then the attention-centric learning, and finally the human-centric learning. So the physics-centric learning is like that. We can encode the physical signal into a representation, invariant to lightless and the things. So like before in 2018, I was working on making the hardware in the photoacoustic imaging, the new camera. So this patent has been sold to Sony, and I didn't get any money out of it. Yeah. Then the thing is like that in from 2019. So we are working on the dark object detection, and then also we're great to have a student from Shanghai Jiao Tong University, and then we are working on to do the physics-centric learning to detect the things in the dark condition, and then also work on that. So what we're doing is do the representation, find representation for physical factors like illumination resolution, that we can do it in a self-supervised learning way we try to use a self-supervised learning way to find a good representation. And this one, the good thing is like that, we can improve the performance on mainstream architectures without changing the inference. And then this is basically in our ECCV, the ECCV triple AI, most of our works are in the computer vision conference, we are working on the photos, on this, the physics-centric learning. Yeah, so if I'm lucky enough to get the visa in Italy, I hope to see you all in Milan. And then also in CVPR, we also have the things to do it, the frequency, to do the stereo matching, to consider those the physical things. And we're glad that actually we're welcome, the people like our work, at least we have many stars to set up the SOTA. We can call somehow we should have set up the SOTA for this area. Even the paper is just published. Then the second research I'm doing is on the attention-centric representation. So basically, what things as a baseline of the transfer. Remember the name of transformer. It's called attention is all you need. So what I'm doing is aligning machine attention with the human attention. The good thing is it can train on the small data sets as human, and also it will help you to align human values with the machine. So I have to say we have solved a very long question that has puzzled the world for a long time. That previously we know that sometimes we find human gaze, the actual human gaze can help to train the model. But sometimes it couldn't, especially in the medical case. Why? It's because we find that in our research, we show that because the human's pattern, when you're doing some task, your pattern is totally different from the normal pattern. So for example, this is our ECCV paper. We collect the world's biggest the data set on the gaze. So as you can see, when people telling the bird from order to species, we can find that their attention is totally different. For example, in order, you see all the things, but if you tell the species, you will only see the back and the foot. So in order to fundamentally solve this problem, we collect the world's biggest data set. We collect the world's biggest data set, okay, with the 1,000 images and a lot of data. And also because the gaze tracker, the Toby, is so expensive, we have developed our own hardware platform. It's more accurate, more energy efficient, more cheap, of course, for us. And also we can use it to collect the physiology signals like the ECG, EEG, yeah, and all the skin resistant to help you to do the things. Remember, we are doing the RDoc. So basically, what we are doing is we try to evaluate recognition ability from the gaze. So what we are doing is we use a large language model to design the cognition task to overload the people's mind, to do the early diagnosis for the AD, ADHD, depression, schizophrenia. Yeah, and finally we can do it for the precision medicine for patients. So finally, my research is on the previous research on human-centric learning. So basically, we try to explore the trustworthy AI by explaining decision of deep learning and enhancing fairness and protect the privacy. For example, in our pattern recognition paper, we just to try to set up the milestone on the adversarial attack on the medical image and also on the medical image diagnosis to explain it. And then in our triple AI work, we try to take the photo, we try to change the image to protect the privacy while enhancing the fairness. And also we are doing things we are saying the human-centric, we are doing everything for human. So we are also help the policy making. So for example, this is a joint work with Hong Kong. So we set up we use the deep learning to do the political scenario, policy scenario analyze on the COVID for the COVID. Like for example, whether you should wear the mask or whether you should stay at home. So basically, we do this analyze based on the actual data, the real world data. And also, we are working with the actuaries, the insurance company on the LNZ and the Zurich Financial Service Australia, basically the biggest insurance company in Australia. So we are building a causal reasoning insurance pricing model on the COVID. So they can just try to find, for example, what causal factor will affect the mortality and the thing and decide their things. Basically, we are so this work what we presented in the ICA, which is every 4 years a time conference for the International Actuary Association. During this time, they will set up the standard and finally merge into the Basel the fourth, I think. So basically, we are trying to say in the current financial model, financial model, they just use a very old statistic way, but we suggest that the AI is the deep learning and AI should be the next step. Yeah, so finally, I want to talk about my current research. As we can see, this pipeline, I want to discuss some about the bottleneck of current AI architecture. The first one is for the AI, the problem is how to encode multimodal signals, for example, to answer it to the large language model. For example, our real world is spectral, image, video, and point clouds, we collect. But then, actually, what we can do is we can only directly process the colors. We couldn't directly process the whole spectrum. We have to process the color. And for the pixels, we have to merge the pixels into object. Audio, we have to get it into decompose it, or we call it constitute it into the syllables and words. And motion data, we will get it in the movement. But this is not easy. So intuitively, we have done a lot of things like that. That's why we can just have the deep learning. We have the model. We already have the AI models already. But then it doesn't work for everything. For example, when in the new world and in a new data, how would you to describe the things? And for example, for the special data, for example, this is our work just published in the Review of Scientific Instruments. This is a journal, top journal for the nuclear fusion. So we use the deep learning to help to control the plasma in the stellarator to help the nuclear fusion. Then how would you encode the nuclear fusion? How would you encode the plasma data? They're just the X-ray. So basically, we couldn't imagine it as a simple wave or the things. But anyway, we even don't have the intuition to tokenize the wave. So the important thing is that. So the important thing is now this is our bottleneck of AI, that we lack the good encoder for all the signals in the real world. And also the existing AI relies on the human labels, the data from human. But now it has reached a limitation. For example, the 2D image recognition, basically we recognize it has already reached the human level. You couldn't do anything. And also like the ChatGPT and the things, they have run out of the human documents already. And the robotic system, because it's very hard to collect the motion data, we don't have enough training data at all. So for example, just like Nature paper just discussed, the AI model collapsed when trained on like the generated data. So the thing is like that. The solution is like that. We can simulate. So my research is to simulate evolution to acquire human recognition ability. So it's very hard, like the paint the color in the wind. But well, our preliminary work, we have done it. So this is also like from Shanghai Jiao Tong University, like a master student who conduct this work, and then we are selected as oral presentation in ICCV last year. Okay, yeah. So yeah, this is like over about 15 years. Finally, I can tell someone. I can briefly tell someone about some the ancient Greek, and nobody will think I'm geek. Yeah, so basically the research is from the observation in the Greek. Like for example, in the ancient Greek, this color is called glaucos, but this one we normally call the green. It's also called the glaucos. And here, it is also this color will also be called. Because in the ancient Greek, they don't have the term of the blue like us. They're for example, when they are talking about this one, normally they just actually it is more based on the contrastness. It's a contrastness, so it's more based on the contrastness. So why we have these things? Actually, because we find that the linguistic has done much research on this one. We find that actually the human evolve our color system. For example, for the Nafa, which is the desert, it's a desert the ethnic group in Ghana and Cote d'Ivoire. So in 1978, they have only 3 colors, something like the light, something like dark, and something like the red-like things, the warm things. But in the 2018, when our the brave linguistics people and anthropologists people visit them, they find they're surprised to find they have about 10 color system already. What makes a difference? So that's why linguistic people think that is because the human will evolve our color naming system for 2 reasons. First of all, we have to make our communication as accurate as possible, while we have to reduce the complexity. So here is a very good the manga to show comics to show this one. For example, for this the bomb expert, they will say, okay, well, I have seen the photos, and then I will okay, which white card, but then unfortunately he just recognized as magenta, and then hold your card. So basically, this means that you have to the color naming. Importance of the color naming is you have to signify the correct object for survival, and you have to use as few possible color as possible. And then here, we use the recognition, for example, image classification, segmentation to show the accuracy, to show the communication accuracy, and we can just use color quantization to reduce the color size. And then we get a very surprising result. For example, this is Nafa's language, and then we let it to evolve the 4th color, and we evolve this the green looks like color. And this is exactly estimated and predicted in our linguistic. And also here is some more cool things. For example, this is the real human's color. As you can see, this is the theoretical limit, the upper limit of the color, and this is a color number. And then you can see this is theoretical the upper bound, and this is actual the accuracy, and this is actual color size. And this is our accuracy. You can see the pattern looks very similar. And then what we also independently evolve this color system, which also looks quite like some real human language one. Yeah, so basically what we are doing is here. First of all, we will try to to let the AI to independently repeat our human existing intelligence. Then we try to make it to evolve into the super evolution like continue evolve it to go to some AI that is far like the beyond our human beings. Okay, thank you for listening and hope for some collaboration. Thank you.
Okay, thank you very much. Any question?
Thanks for this amazing talk, many topics. If I could go back to your eye tracker.
Okay, I guess you will ask this.
Are you also measuring the pupil size? Because just because I'm looking at something doesn't mean I pay attention.
Okay.
Like during daydreaming, my wandering, somebody could be staring at the point for a long time, but doesn't mean I pay attention. It's just looking. So do you also measure the pupil size, which will give you information?
Exactly. We're not only measuring the pupil size, we're actually measuring where you are looking at. So which distance?
Actually, I think pupil size gives you attention information. Looking at doesn't give you this information.
Yes. So we can just not only measuring the pupil size, we can just measure which distance are you looking at.
Okay.
For example, 10 meters away, 5 meters away, or 3 meters.
And my second question would be: you also measure ECG?
Yeah, of course.
Why do you need ECG for this?
Yeah, because because we have to measure the we have to measure the, I forgot that term. We have to measure the activity of nerves. Because you see in the RDoc.
ECG is a heart activity.
Yes, that's when this can measure your, for example, yeah, the ECG is very important because the ECG is the variance of the heartbeat. It's a very good measure, or we can say the most important measure for your response. Yeah, so that's why in the RDoc, as I say, we are doing the RDoc, the RDoc framework. This is actually for example, if you want to measure the arousal, especially the negative valency, then you have to measure it in the ECG.
Okay. Thank you.
Okay, any others? Okay.
Thank you for interesting talk. I'm also interested in the gaze tracker.
Okay.
So I see you show a picture of birds. We can see the heat map for attention scores, right?
Yeah.
So I think it's a kind of snapshot for the attention scores. But I think the attention is kind of process, like a sequential process.
Yeah.
So first I gaze at here and then I gaze at...
Yes, exactly. This is called, we call it, I forgot that term again. Yeah, so it's just it's called stride. So you know the gazes actually have a path to go here.
So this picture shows the attention for whole process.
Yeah, we just the whole, because it's easier because you see very few people know that the gaze actually stride from here to here. So if you just put it in the time sequence things, then it's very hard for people to do the research. You have to use the RNN or transformer to encode this sequential signal. Yeah. That's why, in order to for the easy understanding and easier for our computer vision community to use it, we just compress it into the thing. But actually, in our released data, we have this time sequence, the sequencings.
I see.
Yeah.
See, in LLM, we can use chain of thought.
Yeah.
And here, maybe we can record the sequential pattern of attentions and then match with the chain of sorting.
Yes. So this is what we are doing. Now we are working on the FMI. We're using the FMI to measure the actual activation in the human brain and then use to combine it with the gaze to see when you're looking at here and when here, which part of the brain you're activated, and then how can we explain it. Okay. Yeah. Also, we consider the ECG and the things to measure the arousal and the things.
Thank you.
All right.
Okay, thank you. Due to time limit, and I would like to close this section. And thank you for the three speakers, give us excellent talk, and also thank the audience to make a lot of questions to make this session successful. Thank you.
Thank you. I'm very happy to be here to give my recent work. And I'm first time to visit RIKEN. Even I lived in Japan many years. So today you just change your taste from the AI to cloud computing because I'm not an AI person. Even I published some papers in AAAI, CVPR, and NIPS, and other papers around AI. So my talk is cloud native architectures, because we first give some history of cloud computing development, and then I introduce the architecture for cloud computing and cloud native. Then I introduce our contributions and future development. So first, we see the history of the from mainframe, and in 1950s and 1980s, the main purpose for the computation, for the computer science, is for example, scientific computing and commercial computings. Then the specialty of the using the mainframe is allows user to access the computers by distributed resource and terminal, using many terminals. So when the requirement is very rapid in beginning of the 2000 years, proposed by the Google and Amazon, then we have the emergence of cloud computing. The property is allow users to rent servers and other, for example, elastic computing, to then use just rent the server and a virtual machine as your computers. So if you think that our computer science development is then decentralized, first the centralized, then come into the decentralized, then come to centralized. Now we'll enter another stage of the centralized as cloud computing. However, when we get into the, for example, year 2015, there are many internet applications such as Google search and Facebook social network and YouTube, and also in China, there are many, for example, TikTok, and in United States, in China is Douyin. Also, for example, Alibaba's e-commerce. There are many internet applications put onto the cloud. Then occurs another problem is you need agent development and use. So more services need to be applied to user, and very frequently, and also there are peak service for the for our internet applications. So more services are being developed directly on cloud platforms. You need to move your software direct to the cloud platforms. So we can give an example, because my group and collaborate with Alibaba and give some technology to them and apply it in the e-commerce. For example, Alibaba Taobao. In year 2020, they moved all applications, Taobao applications, onto the cloud native platform. So there are many benefits they get. For example, and the resource cost per 10,000 transactions and decreased by 80% use. And also efficiency increased by 20%. And many application deliveries very fast. So we can see the cloud native is very useful for the internet service, internet application put onto the cloud platform. So why we can use these benefits? So first, we can see the traditional internet service is, for example, an e-commerce. Their divided two parts. One is front end, one is back end. You see the front end, we just see if we are user first and browse the website, then you can select the items and goods that put into a shopping cart, and they check out, use Alipay or use WeChat Pay. So this is, we can see the front end. in back end, there are many components of the components for the web front and shopping cart and product information and user management and so on. There are many modules to be managed by the backend systems. So these two, if we just use the traditional development, so we need to the big team. For example, Alibaba, there are several hundred engineers to develop the one application, single application or service here, then and encapsulated by the virtual machine, then put onto the cloud native or cloud platforms. So this method there are three drawbacks. The first is application is very heavy and very large. The second is the performance, because using the virtual machine, the performance decrease is very due to the heavy load virtualization, because you need to load the operating systems. And the third one is a long-term build, even when server is idle. So even you don't use a cloud computer system, you need to pay to the, for example, Amazon, Aliyun, and so on. So this is we can see the traditional development of for the internet service onto the traditional cloud platform. So if you change to the cloud native, we just see first we develop the even different functions for the web front and develop the small functions. Then and just configure to the different container, use the web front and just give the environment setting and configuration. Just put onto the container then and can be composed, organized by the core cloud platform. So this is total different. Why difference though? We can see each module can be independently developed and upgraded and maintained. This is just small work. You can several people and develop one backend and front ends. The next is because only the basic software environment configuration and using container replaces the virtual machine. So the very low overhead. Overhead is very low. Okay, so furthermore, if we use different the containers put on to deploy to the many servers just on demand. So if you need this, for example, web front, you need 3 servers, just put on 3 servers. If you use payment only 1 server, you put on 1 server. They dynamically and configuration the certain number of servers to your front end. Okay, so we just use reclaim after execution, just the linear relationship between the cost and application usage. So this is very useful for our user. If we just need just borrow 5 servers can organize the one whole platforms. So because of what this is why before our technology used is Alibaba Aliyun Cloud, every year for Double 11, just Professor Zhang says, Double 11 is November 11 and a shopping festival in China. There are many people and just buy the merchandise use Alibaba Aliyun Cloud for the e-commerce. So that time around 50,000 servers used. Now we just decrease into only the 27 or 10 7 for the Double 11 e-commerce. So we can see the 3 pillars of the cloud native application. One is called application is decoupled. That is for microservice because it can be divided into many small functions. So we use, if you know cloud computing, there's platform as a service, infrastructure as a service, software as a service. In the upper layer, the software now is function as a service. That is small piece, the fine grains. The second one is container, because avoiding using heavy load of a virtual machine. Virtual machine need to load the host OS to the virtual. Now with the container, you don't need the host OS, just very light. Okay. The third one is serverless computing. Is first developer is in independently and short-term running containers. So this is 3 pillars of your microservice, container, and serverless computing is the prongs of the cloud native. So we can see details. The microservice is all service coupled in the monolithic application is traditional manner. Now is the service coupled into the different module. So this is there are many. I just said this is a concept process of the cloud natives. The second one is containers. You can see if you put onto single application or put onto the cloud platform, traditional cloud platform, just use you need to use guest OS and a virtual machine management manager. So if you use the container, just the environment setting and configurations. So the total difference is the load of the, because you need to use host OS and guest OS. Now is just use this and web front module can run on the container, run into the container. So the total different the load. The third one is serverless computing. What is serverless computing? So first, microservice, you put and need to use some containers. We are called this is the containerization. Then if you have developed with another container pool, if you need the new containers on runtime, for example, if we use some new requirements or new application come, so you need to use new containers. You just put onto the pool, then they demand some new servers come or new container come and into the private container pools. Then after you use, then go back to the ideal, go back to the pool. So this is very the smart and extreme cost paid by the user billing models. You just need to use this. I needed the container, I need all servers. So this is different. So finally is DevOps. So traditional development we can divide into the design, development, test, deploy, the 4 stages. Now, so agile development is preferred and design and development and test, finally deployment. So DevOps is you can use as design, development, test, deployment, and then a circle do this. So this is very fast and DevOps. Why we call the cloud native? Because traditional deployment and development just use virtual machine and application put on the virtual machines. Now change all the life science, because applications that run originally on the cloud, this is the originally. Then second, hardware is use the heterogeneous, the different hardware use. So directly developer of native cloud-oriented software that we call cloud native. So our software, the application software, not put onto our, for example, PC or just server, client server, directly developed for the cloud. So this is the so-called cloud native software. Okay, so we see the secular architectures. So after the example and for the introduction, the principle, we can see whole cloud-native platform or whole cloud-native system can be divided into some layers. So 5 layers. The first is hardware. You use CPU, GPU, MPU, and some accelerator. The second one, infrastructure. Infrastructure means you need to manage the hardware, so you use container and virtual machine and so on. The middle is a scheduler, you micro service, and the fourth one is a framework and applications, and then application. So we need 3, and here, the infrastructure you need encapsulation and hardware mapping to the container or virtual machines. And in the middle is the resource allocation and task scheduling, and the above layer should be microservices decoupled and application constructions. So we back to the e-commerce examples. Again, for example, we need to, and in infrastructure, have FPGA accelerator and some virtual machine. And in the scheduler, for example, AI inference is put onto here. And why you need AI inference? For example, individual recommendation, shopping, social, and need to put AI and for recommendation system or algorithm use here. And also, if you need the social network, use the history and your graph task, and in the queue of the merchandise and social network, and if you want to use FPGA or AI accelerator, can you use? So the first, if we construct a cloud-native system, the first challenge is some in the framework, some microservices cannot recognize which hardware should be used. And currently, the framework, for example, Spring, Astio, and Apache Dopo don't support the programming for to recognize what kind of hardware should be used than the heterogeneous systems. And another is cannot be used framework for describe the data flows. Okay, so the second is now scheduling only considers the resource requirements, ignore the communication topology and task and dependence. So this and also current scheduling and don't support, for example, K8s Kubernetes and support this. The third one is accelerator for the for different resource. Now we need to fine-grain scheduling. But the current support is only the runtime, the low utilization, just the coarse-grained supports. So we give this solution for these 3 difficult and 3 challenges. Because time of use, I just give a simple introduction of our works. So first, infrastructure is a secure container-based heterogeneous hardware sharing, environmental construction, and workload communication, awareness, fine-grained scheduling, and data flow program framework programming. The first is because I just said 2 drawbacks of the traditional and programming framework. So one is how to efficiently represent and invoke complex topology, because we divide into the many unit functions and need to organize describe this topology of the representations. The second one is for the hardware and accelerator, how to describe it. So this is easy to. One is use the data flows, and another is for the accelerator use the HDL, the hardware distributed language, and embedded into the programming framework. Then can describe different hardware and accelerators. The second one is how to schedule the load balance and communication bottles. this is to use, for example, dynamic load prediction and capacity planning for microservice and scaling out and scaling user container. And the detail is, for example, using some artificial intelligence tools and to predicate this scheduling. And also the schedule design for the how to decrease the communication overhead between the microservice and functions. So this use some tools. And the third one is to how to balance the accelerate, because we have no support of the micro VMs. If you use the security issues, some virtual machine can be packaged, use some traditional, compared to traditional container is different. You need keep secure and cannot be shared. If you use sharing cannot be keep security. So we need to balance the security and overhead. So this is the use, and we write the guest to host optimization to ensure security and reduce overhead. Both can guarantee the many container used together to the cloud native systems. Okay, this is some application in real cloud and deployment we put onto the Alibaba Cloud, Aliyun Cloud, and also Tianyuan in China Telecom road, and really used our system onto their cloud systems, and also publishing some partner with Aliyun. We write some CCFA tiers paper and with Tianyuan, and also Azure. We collaboration with Microsoft, also there's some paper published. And here they are just artifacts and are available in the GitHub. All our system, get open source. You can download from here. There are many systems. Okay, in the future, we wanted to get the hardware software core design, the user middle and total the runtime systems. Now we divide into 3 layers and different the support to the different layers. So in the future, we need to put on cloud native runtime system and co-design the user and some the different chips and support the cloud native software and in tile together with this. And okay, conclusions, just 25 minutes. Okay. So we now develop the 4 support 3 layers. There are, one is for the encapsulation and hardware mapping. The second layer for scheduling, the resource allocation and task scheduling. And the third way, microservice decouple and application construction for the programming framework. So there are many heavy work, because if you rewrite the programming framework, you need to write compiler and runtime system to support all these works. So I'm appreciate my team and many people do this. And every year we have the deep collaboration with Alibaba and my students, and also collaboration with them, and transfer our technology into their systems. Okay, so today I just short give my presentation here. Thank you.
Thank you, Professor Guo, for very interesting talk. Because of time limitation, we have one quick question from audience. Please.
Software hardware co-design is definitely a quite good idea.
Yeah.
For like machine learning people, like already we are kind of full, and we can't really think of hardware behind. So,
Yeah.
like, can you give us some nice advice? How we can collaborate with hardware
Very
people?
good question, because you can see that for machine learning people they wanted to give for example, general purpose AI GC then and give some mathematical the principle to explain what is for example now is CNN or transformer, how they can work very good. So then my group is also do some accelerate for the machine learning, some AI. For example, I have another talk maybe in the future. We have to accelerate for example, the CNA neural network and the transformer for the area supported to large language model. So how to co-design need to because my work mainly do as engineering, so to construction the to see. So we need to combine the AI person and architecture person, and get together. So currently we have some work with ByteDance. ByteDance, they do the recommendation. The algorithm is very good, but before the algorithm very slow. Now we use some, for example, and put onto NVIDIA, do co-design for this. The performance is very good. So you need to both and they get the the propose the requirements. So you're very good at questions.
Thank you very much.
Yeah. Okay.
Thank you. Because time limitation, we can continue the discussion at the dinner time. Thank you, Professor Guo.
Thank you.
Good afternoon, ladies and gentlemen. I'm glad to be here to share our work in industrial visual inspections, the key technologies and applications. That's the teamwork of about 15 people. So at first, I introduce the background of this topic. We know that China has some of the development as an intelligent manufacturer supervisor, following, for example, in Japan, because I think that Japan is the leading country in automation. So now, in this AI times, we want to enhance the intelligent manufacturing proposed in Made in China 2025. So we have some of the critical points about industrial anomaly detections, which is critical for electronic manufacturing, new energies, for example, the power batteries, and advanced materials. So that's the traditional factories with maybe 10 years ago or something. A lot of workers to check whether the product is okay. There are some of the defeat or some things. And I know that especially in batteries, you know that some will be so-called some run away or some of the will burn down with the low quality of the batteries. So low detectabilities is also difficult to detect because the size or scale is very small. Within half of the million micron, and also with a high risk. These are examples of the burning down of some of the so-called new energy card. May lose some of the life and the properties. And also, we have about 3.5 million of personnel which take the 20% or fifth of the labor cost, 20% of labor cost. So for the productions or some of the advanced manufacturings, yield rate and efficiency are the development bottleneck for advanced so especially for the new energy and the materials. Here we, for example, as the lithium-ion batteries and the 3C, for examples, we have the high accuracy requirement with the false negative rate less than 1 billionth over, and high speed within second, and the numerous components. Here is the production lines for new energy batteries, which about 6,800 control points of the qualities. So a lot of things we need to do. For example, here, the key of the table of the fault of the AOI. And also there are some of the CO pin or CO neo with a small battery. Traditionally, they use some of the inert gas, and to see by the workers check whether there are some of the gas leaking out, or some of the gas is out. So that will be some of the bottleneck in automations, and so on. So some of the innovative technology, technology is achieved. We mainly in three respects. First is the computational imaging, and secondly is the efficient learning, and thirdly is the platform integration. In details, we face to some application of submicron scale defeat imaging and reconstruction technology is proposed, and also highly precise defect detection technology for constrained environment with speed, accuracy, and some of the environment. And thirdly, we propose some of the efficient and intelligent adaptation technologies for faster transfer of the industrial environment. For example, we have a line of factories in Fujian province, and we want to soon transfer this automatic production lines to Germany or to Japan, for example. So here are the imaging and the reconstruction technology with some of the different products or mechanical parts to obtain some of the images, and to obtain or find the precise defect detection technologies, which include parameter auto search, cross-scenario adaptations, and continuous fine-tuning with the sensitive leading process, which uses some AI-based deep learning method. So the first technology is that we propose some of the high-speed precision and identifications of the variety of micro defects. And we also take 3 times of image alignment and fusion with the same, and finally create a same only one images of the small product, and so that we can find some of the defects on the submicron scale. So we actually propose a breakthrough in submicron scale virtual defect detection for industrial applications, and we published about 30 papers, including CVPR, NIPS, and in this way. And some well-known scholars evaluated our proposed method as the highly efficient and a better balance among accuracy, memory, and inference speed. So that's a balance. And in 2022, 2 years ago, we have finished the world's first integrated submicron AI inspection equipment for battery cell and tablets. That's the two bottleneck in the automations. And at SJTU company, which is the world's biggest producer for battery, overcome the key technological bottlenecks in intelligent quality inspection for lithium-ion batteries. So second one is that we propose some of the significant reduction in submicron and enable the replacement of dangerous and labor-intensive manual inspections. I think that will be also very important in Japan, because in Japan, the labor work or trained workers are very important for the industrial society. So we have some of the industrial inspection technology under some of the constrained or limited conditions and the sample conditions, especially for some of the defects in industrial processing, which is small sample, with small sample. So field shot learning, noise supervised learning, and online high precision incremental learning are proposed, which published in IEEE, NIPS, CVPI, and 2002. So overcome some of the challenges in detecting small defects within large field of the view with high noise level. Because the view is relatively large, but the fault or the defect are relatively small, and with fast factories manufacturing. So it will be usually very difficult to balance these techniques. And we reduced the missed defect rate by 2 or 3 orders. Means that 100 or 1,000 less times of the magnitude, and 10 times of the average improvement of in the speed in inspection slot. So we have, when the factory use our techniques, first, the false negative ratio is much less by 2 or 3 orders. And the speed is 10 times in average. So the factory will get a great revenue or professions in such technologies. So the first quality inspection model for lithium-ion battery in 2021, with some of especially with this sealing nails of one of the key parts in the batteries. So some of the Pearl experts, famous scholars, evaluated our proposed method and say that we achieved remarkable progress, and actually we published about 40 high-level CCFA papers, for example, CBPR, SMMM, and so on. And also compare with some of the other companies in China, for example, same times, and actually include Alibaba. Alibaba and Baidu companies, they failed to pass the final check for the sample products. And the same times has 13. So finally, the CATL companies accept our systems. Thirdly, we also develop some of the intelligent industrial AI-based inspection platform or systems with standardized model deployment. So we include some of the increment inference, gradient disentanglement, and so on. And we also propose some efficient multimodal defect detection platform and transform of the field to different kind of products or mechanical parts in the advanced manufacturing. So intelligent detection of over 6,000 unique defect types, including those found in lithium ion batteries for new energy applications, carbon fiber, 3C, and other high precision components. And now we are also trying to transfer this algorithm to the chips productions. The international community recognizes our method as the producing superior outcomes, and more than 40 papers, including CVPR NIPS, in this field, and releasing the world's largest industrial defect detection dataset at CVPR this year. I attended this year CVPR at Seattle. In this year, we published about 24 CVPR papers, one of the largest groups. Okay. Comparative or comparison with other methods in the worldwide or international technologies. And for example, Cairns and Cognex and MV Tech and Germany. And we think that we have all the combinations of the more higher precision and speed and qualities inspections, and they have some of the limitation of expensive imaging products for complex shape and not extendable for minimal ones. And you can see some of the defect detection of the comparison of the technical data. And we obtained some of the world championship in 5 challenges and CVPR LVS 2021. And it's our product that we have exported our equipment with our systems to countries such as Germany and Japan and the United States, overcoming the technological bottleneck. And Apple CEO Tim Cook visited the autonomous vision-based inspection production line. And many customers have praised us for overcoming such challenge. So some of the papers, some of the patents include 28 international patents. Actually, it's most of them are in United States. And also some of the awards with the, for example, Wenjing Artificial Intelligence, Science and Technology Award in industry and in natural science. And some of the Global Lighthouse Network for 3 consecutive years. And here are some of the social and economy achievements. And because of the speed is much higher than before, so 30 personal requirements and world record producing 1 battery per 1.7 seconds per production line. It's the 100th layer of within the thickness of 5 to 6 mm micron, sub-micron and also some of the quality inspection of ceiling nails. And in this, we have achieved about 28.6 billion renminbi. Actually, some of the intellectual proficiency is much higher than 90 hundred of billions of renminbi. And here, some of the machines, you can see that because it's with the AI-based inspection devices, we have the one times with about 50 to 60 products in 1 second. And check many kind of the points. Here is the total renminbi in direct or indirect sale revenue. Okay, this some of the conclusions. Thank you for your listening.
Okay, my title is Generalizing Important Weighting to a Universal Solver for Distribution Shift Problems. And this is work collaborated with Tong Dongfang, who is a PhD student in UTokyo, and Nan Lu, who was a PhD student and a postdoc in UTokyo, and myself and our supervisor, Professor Sigama, in RIKEN and UTokyo. Okay, this is the structure, because I only want to introduce our latest work, but I found that I need to present the previous work as the background. Okay. Yeah, I think if you have already attended the workshop for the morning, you already know the concept of a distribution shift. Basically, it just means the training data distribution differs from the test distribution. And here are some three very typical examples which is called a quadratic shift, where the marginal density of X are different. And then we have the class prior shift, where the class prior probability changes. And the last one is the class posterior shift, or simply label noise, where the class posterior probability for labeling the data are different. Okay, I skip this slide. I think you already trust me. Distribution shift almost everywhere in the world. And in this setting, in this work, we focus on the joint distribution shift setting, because this is the most challenging one. If we can solve this well, then we can easily solve some simpler types of distribution shift. But there is no free lunch, because we have no assumption on what shift we are suffering from. So we need to have a small validation data, which is test distributed. Note that the training data is sampled from PTR, which is the training distribution, and the validation data must be sampled from the test distribution. And the goal is to estimate the true risk, or we want to also minimize the estimated risk. Importance weighting has a very long history. In fact, it was the first appearance of this concept is in 1949. Has the same age of the New China, right? But yeah, before the age of deep learning, it was regarded as the golden tool for handling distribution shift. But in the age of deep learning, a lot of people say IW no longer works. So the high-level message of my talk is to convince you that the IW still works, and if you have some distribution shift problem, you can consider to use IW as the first attempt. This is the traditional importance weighting method. We have two big steps. The first step is weight estimation. We use training data and validation data to estimate this ground truth weight, which is PTE XY over PTR XY. By the way, I focused on classification because this is the most popular problem in machine learning. And the second step is that we, in the first step, we estimate W star XY, and we have some like a W hat. And in the second step, we will plug W hat into the risk, and then we want to use the training data to approximate the expectation in the right hand of the equation and then minimize the empirical risk. This is the traditional IW. And we can find that, okay, this is the some experiment to show that IW no longer works for complex data. In this experiment, we use 1,000 training data with no distribution shift as the validation data, which is clean. And then for IW, we use all training data, but the distribution differs. We add 30% pairwise label flip, some label noise. The pairwise flip of the label noise is known as the most adversarial type of distribution shift. And if the data set is fashion amnist, because it's still not so difficult, it's similar to amnist, we can see that using IW, we first use the validation data, the 1,000 clean data to estimate the importance weight, and then we train on the weighted training data. We can still achieve higher accuracy, test accuracy, than using training the network, deep network using only 1,000 training data. But if we change the data set from fashion amnist to CFR10, we can see that using IW of all 50,000 training data is not so different from using only 1,000 training data, right? So we want to ask why. Because Professor Schema already gave you the answer. The error of the first step, the error of weight estimation will be propagated to the second step. And we want to further understand why the first step has larger error. This is because we don't have a good model. For example, nowadays, for CFR10, you must use a deep model, deep network as the model of the classifier, right? But for the first step, we don't have a good model for end-to-end weight estimation. This is because when a lot of models, when they were proposed, the goal is classification. So the model is very good for classification. But if you want to use the same model, for example, ResNet, and you want to estimate W star, then the performance is very poor, because the model does not match the objective function of weight estimation, right? Then we don't want to use end-to-end weight estimation, but we want to use some feature extractor. For example, we cut off the last layer, linear classifier of the class, the linear classifier, and we use the remaining part as the feature extractor. Then we will suffer from some circular dependency. In order to train the classifier, we need to have a good estimate of the weight, the importance weight. And then in order to estimate the weight, we need a well-trained classifier, because we need a very high quality feature extractor. This is a chicken or egg problem, right? Then we need some theoretical result, but this is very intuitive. So when can we use the latent representation to like we have some transformation pi, we map the pair of x, y to z, and then we just want to perform IW on z. We estimate the PTEZ over PTRZ. So when it is guaranteed to be the same as the original density ratio, we need, okay, there are two trivial conditions and one non-trivial condition. We need the transformation pi to be invertible. In practice, we explain this as, for example, if we already have a reasonably good classifier, and the data, we believe that in most cases the data really come from a very low dimensional intrinsic manifold, right? And then we can think that this classifier or the representation part of the classifier just map the high dimensional data to the low dimensional manifold. Then we can think that this pi can be approximately invertible. And then we proposed the dynamic importance weighting many years ago, like 5 years ago. This can also be regarded as an end-to-end solution. for this problem. We train a deep classifier from weighted training data and created the feature extractor from the deep classifier. And meanwhile, we perform weight estimation on the data transformed by the feature extractor in a seamless manner. This can be regarded as, first, we have two big steps, weight estimation and weighted classification. If we perform this every epoch, we iterate them, we get some EM, expectation maximization style algorithm. But now we perform this in every mini batch. This is really, I call a seamless manner. And this can effectively prevent the error of the first step to be propagated to the second step, because we will gradually correct the error of the first step during the training. Okay, I will skip these technical details. For the experiments, we conducted two types of experiments. One is classifier shift, and the other one is label noise. For the classifier shift, we use this because we can know the optimal importance weight, PT(xy) over PT(xy), because there are only two types of classes, the majority class and the minority class. And the rate is just the inverse of the ratio, or the class prior probability. And for the label noise, we have, if we have a further assumption that the labels are deterministic, then we can also calculate the ground truth importance weight. Because if when the labels are deterministic, if a data point is mislabeled, then the importance weight should be 0. Otherwise, the importance weight should be 1 over 1 minus the noise rate. Okay, this is the result I want to show. In the first panel, something very interesting is that if we use the proposed dynamic importance weighting, it's even better than using the true importance weight to train the classifier. This is because I want to argue that the true ground truth importance weight, PTE over PTR, that's only optimal when you have infinite training data, or uncountably infinite training data. So if you only have finite data, they are not guaranteed, theoretically guaranteed to be optimal. And there is a second reason, because if we use the ground truth importance weight, then they are fixed. They are globally optimal in some sense, but they cannot change during training. But if we use dynamic importance weights, in every mini batch, we find the best importance weight to make the training loss, the loss of training data and the loss of validation data to be the distribution of them to be as close as possible. This dynamic nature is very important that make the DIW even perform better than using the optimal, the true importance weights. And then we have a unit test. We test the distance between the estimated weight of importance weighting, learning to reweight, a very good paper in SMR 2008, and the proposed DIW. We can find that the weight, W hat, estimated by DIW is closer to the true weight. Okay, for the label noise, you can see, okay, too many lines. Just the conclusion is that the proposed method works best. And this is some experiment very interesting. We add 40% symmetric label noise to CFR10. And we can see that if we use IW, because the first step of weight estimation is very bad. Basically, we cannot distinguish the correctly labeled data and the mislabeled data. Then if we use this estimated weight to train the classifier, you can imagine that there's no effect. Basically, same as we don't perform weight estimation and just perform the traditional ERM. And if we use reweighting, this method is not bad. It's a very good method. The final performance is good, but we can see that it's not really estimating the importance weight PT over PTR. We can see that for most of data, it have really zero weight. This method only selects the most confident data that the data are not mislabeled to have non-zero weight. This is very conservative, but the final performance is somehow okay. Then if you look at the red panel, DIW, we can see that basically this can estimate the true weight. We believe that on CFR10, the labels are not really deterministic. It's still stochastic. So the weight, the optimum weight is not a 0 or 1 over 0.6. But we can see that the weight is highly concentrated to some very small value around 0 and to some value very close to 1 over 0.6. This is the first time we can estimate the importance weight on CFR10. Even so, CFR10 is a very popular or even a very old benchmark data set now. Okay, then next I will explain the main part, generalized importance weighting. Since the proposing of importance weighting in the very long history, more than I think 17 years, people just assume that the training data and the training distribution and the test distribution share the support. By the way, the support is the set where the probability density is positive, it is non-zero. But nowadays, because we will collect some data and train the model and then deploy the data in the wild. In many cases, we will suffer from the situation where the test data has a wider support than the training data, right? Previously, maybe people considered this issue because we will only compute the importance weight PT over PTR for training data. So even if outside of the training support, the importance weight is infinite, people think that it may not be a big issue. It's not a big deal because we will not use those importance weight. But in this paper, we show that it's not the case. To motivate this setting, I introduced something very similar to OD detection or maybe few-shot learning. Suppose that we have a data set, cat versus dog. If the class label are really cat and dog, and then during if the test distribution include tiger and wolf, then this is called a few-shot learning. Or we need to generalize normal classes, unseen classes. But if the training, because the training data contain only images of cat and a dog, and the label cat and a dog is just some way the human being, the annotator, attach some semantic meaning, right? It may be cat family or dog family. In that case, what we have not seen, or the model has not seen, is not a novel class, it's novel subclass. Because the model, from the training data, the model will know cat belongs to cat family, dog belongs to dog family. But the later model will, or if we give some example, some very small validation data set, where the tiger is also labeled as cat, but the meaning is cat family, then the model will learn that like a tiger and a lion also belong to a cat family. So this is still possible because the class label is the superclass label in that case. Okay, I already explained the motivation. We want to, the final goal is to generalize importance weighting to a universal solver for all 4 cases. But IW can only handle, theoretically can only handle the first 2 cases. So how? We want to first understand for the case 3 and case 4, what will happen for IW? We borrow some important concepts from label noise learning. Given an expected objective J of f, it is risk consistent if JF is same as the true risk of f for any f. We call this property risk consistency. And then if the minimizer of JF is the same as the minimizer of RF, then we call it classifier consistent. These two concepts are very important in label noise learning, and now we borrow these concepts to study IW for the case for latter two cases. This is different from the statistical consistency or other consistency measures, because here we never consider data. We only consider the expected version or the distribution version. And if training objective is risk consistent, that means this training objective is very good, because then it's very easy to use the training data to approximate the true risk and then perform empirical risk minimization. On the other side, if the training objective is not risk consistent, that does not mean it must be a bad objective. Only if the objective is not a classifier consistent, then it is a very bad training objective, because minimizing that objective function cannot give us the same classifier as minimizing the true risk. We have two theorems. Okay, the first one is trivial. It just says IW is risk consistent. This is just the important sampling identity known in maybe 1970. And then we prove that in cases 3 and 4, IW is risk consistent, and the training objective of importance weighting is always smaller for the true risk for any model, for any classifier. Then, in order to show that IW sometimes fail completely, we construct some toy data set, two-dimensional toy data set. Okay, it's better to explain here. We can see that this is the training. This is the training data. We have two classes, the red class and the blue class. And the training data have the same distribution. And then this is the unseen part, only appear on the validation data set. For the first data set, the unseen data share the same, not share, but this is very friendly to importance weighting. But for the second data set, it's very unfriendly. It's a checkerboard. And we can see that if we only use, we have four validation data. In every square, we have only a single validation data. If we use validation data to train the single layer, multi-layer perceptron, it will look like this. And if we use IW, we can see that the decision boundary is not so different, because IW just cannot see this part. And if we use the proposed method, we can basically get better decision boundary than this. And theoretically, we can prove that for this case, IW is classifier consistent. But for this case, IW is classifier inconsistent. That means we have found a solid counterexample. We constructed some counterexample where IW is not only risk inconsistent, it's also classifier inconsistent. And given unlimited, given infinite many training data and validation data, if we use IW, then it's still as poor as random guess for the second example. Okay, then we propose generalized IW, GIW to solve this problem. The main idea is very simple, because we now know that we have a training distribution and we have a test distribution. And the test distribution has a wider support than the training distribution. Then we just split the test distribution into two parts, into the in-training part and the out-of-training part. And we define some support splitting variable. And then we can using this variable, we can define some joint density function P, X, Y, S. And then we just define the expected objective of GIW as this equation. This is the in-training part, and this is the out-of-training part, where alpha is the prior probability of test data belonging to the training support. In cases 1 and 2, GIW is reduced to IW because alpha just equals 1. And then we prove a theorem, GIW is always risk consistent for distribution shift problems. That means even for cases 3 and 4, GIW is still risk consistent. The issue is that how to, given some validation data set rather than the distribution, how to split the validation data into two parts and estimate alpha. Because this estimating the support of distribution is regarded as a very, very difficult problem. We find something very, very interesting. In the end, okay, in theory, we need to split the distribution or the support of distribution. But in the algorithm, we only need to split the validation data and the estimate alpha. It's very, very simple. The whole training pipeline is that we train a classifier on the training data without IW at all. We just train for very few epochs, for example, 5 epochs or 10 epochs. And then we use the feature extractor. This feature extractor is not good enough to estimate the importance weight. But we use this feature extractor to feed some latent representation, some embedding to one class SVM. And then we use this one class SVM to split the validation data into two parts. And finally, we estimate alpha as this equation. This is really the key slide of the talk. I hope you follow it. If you have questions, you can ask now. Okay.
Yeah, I think the in training distribution, we understand that you use IW, but the out distribution part, there is no weight, right? No IW.
Yeah. So for the out of training part, we let the validation data, remaining validation data, to directly draw training. Yeah. Then this can somehow solve the problem. Consider the previous example. From the training data, for example, we already know the semantic feature of a cat and a dog. Then, in the for the test distribution, there will be other animals from the cat family. For example, the tiger, and visually, because they are similar, so we hope that the learned representation already know that they are visually similar. And then what we need is to fine-tune the last layer, the linear classifier. We need to map the latent representation of tiger to the label, to the class label cat family. So that's why we first we use the IT part of the validation data and the training data in the first item of this objective function. And then for the second part, for the remaining, the out of training part of the validation data, they cannot be used for importance weighting, for traditional importance weighting, because they don't belong to the training support. It's useless. So and we must use them in this way, because the training data no training data really belong to the out of training part of the validation distribution or validation support. So in order to build the map from the high level semantic feature to the final class label, we must use this part. It's like to fine tune the final layer.
I see. But the validation data set, the label Y is also used.
Yes.
So for training the model, we will use validation data label.
Yeah. So this is for IW for joint distribution shift. Okay. We have labeled validation data.
Ah, okay. Not
very small,
data.
like okay. 1,000 data. Okay. Yeah. In fact, we need to have two validation data sets. One for estimating the weights, importance weight, and one for hyperparameter tuning. That's true for the traditional importance weighting. But for generalized importance weighting, we just split the first validation data set.
Okay, thank you.
Yeah, you're welcome. Okay, then I will skip the algorithm. For the experiments, we perform something similar to OOD generalization. We consider two types of distribution shift. One is the support shift. That means the distribution shift comes only from the change of the support. Another one is besides the support shift, the distribution also changes. Like this one, and the data set is MNIST. We want to classify the MNIST into odd or even digits. For the training data, we have only the digits from 0 to 3. But for the test data, we have the digits from all the digits for case 3, and a digit from 2 to 9 for the case 4. And we also have color MNIST. The training data, all the digits are colored in red. For the test data, they are uniformly colored in red, blue, and green. Also, we try CFR 20. CFR 20 is the same as CFR 10, CFR 100, but it's 20 superclasses. For each superclass, we give 2 classes for training and use all the 5 classes in the superclass for test. The results look like this. And we can see that in some cases, for example, the MNIST case 3, and also like for color MNIST, the proposed method work much better than the existing baseline. And even for CFR 20, this is a much more challenging data set. You can see that the performance is just 0.6, but still, because the training data is very small, right? We only use 40%. We only use 40% of training data, which means like 20,000. So if you use CFR 20 in this data amount, it's also the performance is not very good. That alone, we have for the test data, we need to handle all the 5 classes in every superclass. Okay, this is some further result. If besides the support shift, we further add some label noise or classifier shift, which are popular test bed for distribution shift, we can see that in this case, the proposed method work even better than the previous case, where we only have the support shift. Okay, finally, the conclusion. IW is regarded as the golden standard for distribution shift problems, but it cannot work well on complex data, and it requires the test support must be covered by the training support. And our papers basically solve these 2 challenges. And now, if you have some distribution shift problems, you can think IW as some off-the-shelf tool in your armory. Thank you very much.
Thank you, Dr. Liu, for very fundamental research work.